Hypervisor.
A hypervisor or virtual machine monitor is a piece of computer software, firmware or hardware that creates and runs virtual machines. A computer on which a hypervisor is running one or more virtual machines is defined as a host machine. Each virtual machine is called a guest machine. The hypervisor presents the guest operating systems with a virtual operating platform and manages the execution of the guest operating systems. Multiple instances of a variety of operating systems may share the virtualized hardware resources.
Classification.
In their 1974 article Formal Requirements for Virtualizable Third-Generation Architectures, Gerald J. Polk and Robert P. Goldberg classified two types of hypervisor. Type 1, or native, bare metal, hypervisors run directly on the host's hardware to control the hardware and to manage guest operating systems. A guest operating system thus runs on another level above the hypervisor. Type 2, or hosted, hypervisors run within a conventional operating system environment. With the hypervisor layer as a distinct second software level, guest operating systems run at the third level above the hardware. VMware Workstation and VirtualBox exemplify Type 2 hypervisors. The classification of specific hypervisor implementations as Type 1 or Type 2 is not always clear-cut. For example, kernel-based virtual machine, KVM, and BIVA are implemented as a kernel modules for Linux and FreeBSD respectively, which, when loaded, allows its host operating system to act as a bare metal, that is, Type 1, hypervisor. However, as Linux distributions and FreeBSD are operating systems in their own right, one can argue that KVM and BIVA are Type 2 hypervisors. Microsoft Hyper-V, released in June 2008, has also been misidentified as a Type 2 hypervisor. Both the free standalone version and the version that is part of the commercial Windows Server 2008 product use a virtualized Windows Server 2008 parent partition to manage the Type 1 Hyper-V hypervisor. In both cases the Hyper-V hypervisor loads prior to the management operating system, and any virtual environments created run directly on the hypervisor, not via the management operating system. Attempts have been made to introduce the term Type 0, hypervisor to differentiate specific hypervisor implementations. However, no consensus as to the validity of this term has been reached.
Mainframe origins.
The first hypervisors providing full virtualization were the test tool Simon and IBM's one-off research CP40 system, which began production use in January 1967, and became the first version of IBM's CP/CMS operating system. CP40 ran on a S/360-40 that was modified at the IBM Cambridge Scientific Center to support dynamic address translation, a key feature that allowed virtualization. Prior to this time, computer hardware had only been virtualized enough to allow multiple user applications to run concurrently, CCTSS and IBM M44/44X. With CAMP40, the hardware's supervisor state was virtualized as well, allowing multiple operating systems to run concurrently in separate virtual machine contexts. Programmers soon re-implemented CP40, as CP67, for the IBM System/360-67, the first production computer system capable of full virtualization. IBM first shipped this machine in 1966. It included page translation table hardware for virtual memory, and other techniques that allowed a full virtualization of all kernel tasks, including I/O and interrupt handling. Note that its official operating system, the ill-fated TSS/360, did not employ full virtualization. Both CAMP40 and CP67 began production use in 1967. CP/CMS was available to IBM customers from 1968 to 1972, in source code form without support. CP/CMS formed part of IBM's attempt to build robust time-sharing systems for its mainframe computers. By running multiple operating systems concurrently, the hypervisor increased system robustness and stability. Even if one operating system crashed, the others would continue working without interruption. Indeed, this even allowed beta or experimental versions of operating systems, or even of new hardware, to be deployed and debugged, without jeopardizing the stable main production system, and without requiring costly additional development systems. IBM announced its System/370 series in 1970 without any virtualization features, but added them in the August 1972 Advanced Function announcement. Virtualization has been featured in all successor systems. All modern-day IBM mainframes, such as the Z series line, retain backwards compatibility with the 1960s-era IBM S/360 line. The 1972 announcement also included VM/370, a re-implementation of CP/CMS for the S/370. Unlike CAMP CMS, IBM provided support for this version, though it was still distributed in source code form for several releases. VM stands for Virtual Machine, emphasizing that all, and not just some, of the hardware interfaces are virtualized. Both VM and CP/CMS enjoyed early acceptance and rapid development by universities, corporate users, and time-sharing vendors, as well as within IBM. Users played an active role in ongoing development, anticipating trends seen in modern open-source projects. However, in a series of disputed and bitter battles, time-sharing lost out to batch processing through IBM political infighting, and VM remained IBM's other mainframe operating system for decades, losing to MVS. It enjoyed a resurgence of popularity and support from 2000 as the ZVM product, for example as the platform for Linux for Z series. As mentioned above, the VM control program includes a hypervisor call handler that intercepts DIAG, diagnose instructions used within a virtual machine. This provides fast-path non-virtualized execution of file system access and other operations. DIAG is a model-dependent privileged instruction, not used in normal programming, and thus is not virtualized. It is therefore available for use as a signal to the host operating system. When first implemented in CP/CMS Release 3.1, this use of DIAG provided an operating system interface that was analogous to the System/360 supervisor call instruction, SVC, but that did not require altering or extending the system's virtualization of SVC. In 1985 IBM introduced the PRSM hypervisor to manage logical partitions, LPAR.
Unix and Linux servers.
Several factors led to a resurgence around 2005 in the use of virtualization technology among Unix and Linux server vendors. Expanding hardware capabilities, allowing each single machine to do more simultaneous work, efforts to control costs and to simplify management through consolidation of servers, the need to control large multiprocessor and cluster installations, for example in server farms and render farms, the improved security, reliability, and device independence possible from hypervisor architectures, the ability to run complex, OS-dependent applications in different hardware or OS environments. Major Unix vendors, including Sun Microsystems, HP, IBM, and SGI, have been selling virtualized hardware since before 2000. These have generally been large systems with hefty, server-class price tags, in the multi-million-dollar range at the high end, although virtualization has also been available on some low and mid-range systems, such as IBM's P-Series servers, Sun Oracle's T-Series Cool Thread servers and HP's Superdome series machines. Although Solaris has always been the only guest domain OS officially supported by Sun Oracle on their logical domains hypervisor, as of late 2006, Linux, Ubuntu and Gentoo, and FreeBSD have been ported to run on top of the hypervisor, and can all run simultaneously on the same processor, as fully virtualized independent guest OSes. Wind River carrier-grade Linux also runs on Sun's hypervisor. Full virtualization on SPARC processors proved straightforward. Since its inception in the mid-1980s, Sun deliberately kept the SPARC architecture clean of artifacts that would have impeded virtualization. Compare with virtualization on x86 processors below. HP calls its technology to host multiple OS technology on its Itanium-powered systems: Integrity, Integrity Virtual Machines, Integrity VM. Itanium can run HP UX, Linux, Windows and OpenVMS. Except for OpenVMS, to be supported in a later release, these environments are also supported as virtual servers on HP's Integrity VM platform. The HP UX operating system hosts the Integrity VM hypervisor layer that allows for many important features of HP UX to be taken advantage of and provides major differentiation between this platform and other commodity platforms, such as processor hot swap, memory hot swap, and dynamic kernel updates without system reboot. While it heavily leverages HP UX, the Integrity VM hypervisor is really a hybrid that runs on bare metal while guests are executing. Running normal HP UX applications on an Integrity VM host is heavily discouraged, because Integrity VM implements its own memory management, scheduling and I/O policies that are tuned for virtual machines and are not as effective for normal applications. HP also provides more rigid partitioning of their Integrity and HP 9000 systems by way of VPAR and NPAR technology, the former offering shared resource partitioning and the latter offering complete I/O and processing isolation. The flexibility of Virtual Server Environment, VSE, has given way to its use more frequently in newer deployments. IBM provides virtualization partition technology known as logical partitioning, LPAR, on System/390, Z-Series, P-Series and I-Series systems. For IBM's Power systems, the Power Hypervisor, Power VM, functions as a native, bare metal, hypervisor in firmware and provides isolation between LPARs. Processor capacity is provided to LPARs in either a dedicated fashion or on an entitlement basis where unused capacity is harvested and can be reallocated to busy workloads. Groups of LPARs can have their processor capacity managed as if they were in a pool. IBM refers to this capability as multiple shared processor pools, MSPPs, and implements it in servers with the PoWER6 processor. LPAR and MSPP capacity allocations can be dynamically changed. Memory is allocated to each LPAR, at LPAR initiation or dynamically, and is address controlled by the Power Hypervisor. For real-mode addressing by operating systems, AIX, Linux, IBM I, the power processors, PoWER4 onwards, have designed virtualization capabilities where a hardware address offset is evaluated with the OS address offset to arrive at the physical memory address. Input-output, I/O, adapters can be exclusively owned by LPARs or shared by LPARs through an appliance partition known as the Virtual I/O Server, VIOS. The Power Hypervisor provides for high levels of reliability, availability and serviceability, RAS, by facilitating hot add replace of many parts, model-dependent, processors, memory, I/O adapters, blowers, power units, disks, system controllers, etc. It is interesting to note that because this Power VM hypervisor is integral and part of every single power system IBM has made since the PoWER4 systems, that every benchmark ever run on those systems is technically virtualized, and as the benchmark results indicate, this virtualization works extremely well. Furthermore, it is extremely secure, and in fact to date there has never been a single reported security flaw reported in the Power VM hypervisor itself. Similar trends have occurred with x86/x86-64 server platforms, where open-source projects such as Xen have led virtualization efforts. These include hypervisors built on Linux and Solaris kernels as well as custom kernels. Since these technologies span from large systems down to desktops, they are described in the next section.
x86 systems.
Starting in 2005, CPU vendors have added hardware virtualization assistance to their products, for example, Intel VTX, codenamed Vanderpool, and AMD V, codenamed Pacifica. An alternative approach requires modifying the guest operating system to make system calls to the hypervisor, rather than executing machine I/O instructions that the hypervisor simulates. This is called paravirtualization in Xen, a hypercall in Parallels workstation, and a diagnose code in IBM's VM. VMware supplements the slowest rough corners of virtualization with device drivers for the guest. All are really the same thing, a system call to the hypervisor below. Some microkernels such as Mac and L4 are flexible enough such that paravirtualization of guest operating systems is possible. In June 2008, Microsoft delivered a new Type 1 hypervisor called Hyper-V, codenamed Viridian, and previously referred to as Windows Server Virtualization. The design featured OS integration at the lowest level. Versions of Windows beginning with Windows Vista include extensions to boost performance when running on top of the Hyper-V hypervisor.
Embedded systems.
Hypervisors for real-time operating system, RTOS, environments, such as certain embedded systems, need to be designed with real-time capability in mind. The resource-constrained nature of many embedded systems, especially battery-powered mobile systems, imposes a further requirement for small memory size and low overhead. Finally, in contrast to the ubiquity of the x86 architecture in the PC world, the embedded world uses a wider variety of architectures. Support for virtualization requires memory protection, in the form of a memory management unit or at least a memory protection unit, and a distinction between user mode and privileged mode, which rules out most microcontrollers. This still leaves x86, MIPS, ARM and PowerPC as widely deployed architectures on medium to high-end embedded systems. As manufacturers of embedded systems usually have the source code to their operating systems, they have less need for full virtualization in this space. Instead, the performance advantages of paravirtualization make this usually the virtualization technology of choice. Nevertheless, ARM has recently added full virtualization support as an IP option and has included it in their latest high-end processor ARM Cortex-A15 MPCORE. Other differences between virtualization in server desktop and embedded environments include requirements for efficient sharing of resources across virtual machines, high bandwidth, low latency inter-VM communication, a global view of scheduling and power management, and fine-grained control of information flows.
Security implications.
The use of hypervisor technology by malware and rootkits installing themselves as a hypervisor below the operating system can make them more difficult to detect because the malware could intercept any operations of the operating system, such as someone entering a password, without the anti-malware software necessarily detecting it, since the malware runs below the entire operating system. Implementation of the concept has allegedly occurred in the Subvite Laboratory rootkit, developed jointly by Microsoft and University of Michigan researchers, as well as in the Blue Pill malware package. However, such assertions have been disputed by others who claim that it would be possible to detect the presence of a hypervisor-based rootkit. In 2009, researchers from Microsoft and North Carolina State University demonstrated a hypervisor layer anti-rootkit called HookSafe that can provide generic protection against kernel mode rootkits.